activity. He tries to organize or support activities outside India. Yeah, so he doesn't come to PEDES also, although PEDES is IES conference. He so yeah, within India, if somebody is more inclined for IES, is Professor Gopa Kumar from IISc.
गोपा कुमार,
Professor Gopa Kumar, yeah. So
हमको अगर कांटेक्ट उनका दे देंगे बाद में, देन वी मे हेल्प.
हाँ, yes sir, I will connect. हाँ, तो इंडिया में तो जनरली 2 है, और अनदर वन इज रितेश केसरी, लाइक जो प्रद्युम्न के साथ है. हाँ, रितेश केसरी. सो ही इज IES, वो उन्हीं का स्टूडेंट भी था, प्रोफेसर बूजा जो है ना इटाली में.
ओहो, अच्छा, ओके.
हाँ, गिसेपी बूजा जो यूनिवर्सिटी ऑफ पेडोवा में थे. तो yeah, so when I was in IES Society Transportation Rectification Committee chair, then I pulled Ritesh in, and then after me Ritesh took over. Yeah, so he is there. Pradyumna is in PELS also, and IES also. Yeah, but IES is really focusing because number of chapters are a lot now in India in IES. So like in chapter and membership development committee meeting, IES was quite happy on that. That number of membership in India is increasing on for IES, and the chapters are also increasing, number of chapters, joint chapters.
I'll introduce to one of my friend, Tanmay Pal. He's Tanmay. Are you listening me? Tanmay. And Dr. Silent Samaj is here. Maybe we can start in few.
Yes, sir. Yes, sir. We should start now.
I just like to bring out that a couple of my friends are doing from Indian Institute of Corporate Affairs Impact Leader course on ESG. Some of them I find Mr. Anand Kulkarni has joined. I'd say thank you, Mr. Badapanda, that he said that it's open invitation because it's such an interesting topic that others may like to join. So I took this opportunity to invite my colleagues. Thank you so much.
Sure. Dr. Kulkarni, can you introduce Kulkarni introduction? Dr. Kulkarni, am I audible to you?
Yes, sir. I am in the Navy, sir. And after 26 years of service in the Navy now, I am doing my transition to the civilian world. So I am due to retire in the month of August. And I am from the executive branch. So I've been looking after the the weapons part of the Navy, and this is a completely different field that I'm getting into now. I'm trying to acclimatize myself and reskill myself. So any opportunity that is provided, I just I'm up for grabs. I take it up, whatever is coming through my way. So I found this to be a very interesting topic, and that's why I joined it.
Yeah, it is very interesting now, specifically not only in Indian context and worldwide also. So maybe we do conduct every month 2 lectures. Maybe you can give your contact detail. Whenever you do that, we'll just forward to you as well.
Absolutely, sir. Absolutely. That will be great, sir. Thanks.
Okay, sir. We will start now.
Yeah, sure.
Okay. I welcome you all on the occasion of this lecture. I am Akshay Tripathi, Secretary of PLS IES chapter and IRC of IEEE Madhya Pradesh section. I welcome Dr. Akshay Rathore, who has kindly agreed to give this lecture on a very novel topic, which is hydrogen energy, global trends and opportunities in India for transportation. I also welcome Mr. Badapanda, sir, who is the chair of PLS and IS chapter and IRC of IEEE Madhya Pradesh section, who is actually basically looking after all the activities of this chapters and this IRC. I welcome Dr. Das, sir, who is here. We are fortunate to have him. And I also welcome Dr. Trapti Jain and others and other participants. Now I request Dr. Mathur to give a brief introduction of Dr. Akshay Rathore. And I request all the participants that if you have any questions regarding this lecture, they may write in the chat box, which will be taken at the end of this lecture by my colleague, Mrs. Rinki, at the end of this lecture. It's over to you, Dr. Mathur.
Thank you so much, Akhilesh sir. Good evening, everyone. This is Shravani Mathur, Secretary, PELS, chapter of Madhya Pradesh section, India. I would like to introduce today's speaker. It's my privilege to introduce Dr. Akshay Kumar Rathore. He's an IEEE fellow. He's an expert in power electronics and controls of electrical motor drives. He received the gold medal for securing the highest academic standing in his master's degree among all electrical engineering specializations at Indian Institute of Technology, BHU Varanasi. He had two subsequent postdoctoral research appointments with the University of Wuppertal, Germany, in the year 2008 to 2009, and University of Illinois at Chicago, USA, in the year 2009 to 10. From November 2010 to February 2016, he served as assistant professor at National University of Singapore. From March 2016 to December 2021, he served as an associate professor at Department of Electrical and Computer Engineering, Concordia University, Montreal, Canada, where he was listed in Provost Circle of Distinction. So I would like to deliver the mic to Dr. Akshay Rathore, sir. Sir, please start.
Thank you, Dr. Mathur, and thank you all the attendees. So very good evening. I will just share my screen. Can see the screen now?
Yes, it is visible.
Yeah, and are the slides moving?
Yes, yes.
Yes, okay. Yeah, I always ask these first two questions. Yeah. So I will just go through. It's a quite simple topic, not much on technologies, more about opportunities in India and the global developments about hydrogen energy. Okay, so let's start that majority of the countries or the governments, they are investing a lot on either renewable generation, alternative energy, or transportation electrification, which is electric mobility. Okay, so majority of the universities like IITs and ITs there and in overseas, when it goes to electrical department and mechanical department and all, majority of them are working on either renewable energy, smart grid, microgrid, or electric vehicles. Okay, so here is the reason that majority of the carbon footprint in the environment, which is 3/4, more than 75%, is due to electrical power generation or due to the transportation sectors. Okay, by 2050 there is a commitment of majority of 2050, sorry, 2050, majority of the countries in various summits, international summits, they have basically committed to reduce carbon emission by 80%. That okay, we will cut down carbon emission from our resources by 80%. Okay, so here it is that if you control these two, 75% is basically reduced. That is the reason that majority of the governments, countries, universities, they are fully focusing on alternative energy or electric transportation. Okay, according to Niti Aayog last year, they said that pollution in India due to transportation is around 15%, which is quite optimistic. Okay, but it is very close to 20 or 20 plus even. Okay, because majority of our vehicles are gasoline vehicles. Okay. Yeah. So if we see, this is the current scenario that in India, if we say that in entire world, the total number of registered vehicles are 1.4 billion, then in India, the share is 300 millions. Okay. Yeah, 300 millions, quite a lot, 30 crores. Okay. And right now, the number of electric vehicles in India are very close to basically 2 crores, which we can say approximately 7%. Okay, 93% are still gasoline based. Okay, now electric transportation is happening. Okay, governments are trying basically that okay, after 2030 they will stop registering gasoline vehicles. Okay, or from 2040 they will scrap all diesel and petroleum vehicles, it will be only electric. Okay, but things are moving because standards have to come, infrastructure have to come, okay, policies have to come for many things. Okay? So electrification is possible in two ways: either it is battery based electrical mobility, or hydrogen fuel cell based electric mobility. Okay, both are electric vehicles, only the source is different. So generally electric vehicles have basically three major components as a propulsion system or the traction system. One is the source, which is battery, then inverter converting DC into AC, and then after that induction motor. Okay, similarly in hydrogen fuel cell vehicle, it is a fuel cell converting hydrogen into DC, and then inverter which is converting DC to three-phase AC, and then the motor. So only the difference is the source, either battery is the source or hydrogen fuel cell is the source. Okay, for both the cases there are different challenges. When it comes to batteries, there are many challenges we will see. Okay, but one of the major challenges, charging infrastructure and fast recharging. Okay, how can you charge your battery very fast so that you can go, suppose, from one city to another? If you want to go from Indore to Bhopal, it takes 3 hours, but probably you need to stop somewhere and to charge, because after 100 or 110 kilometers, Mahindra E2O Plus will stop. The mileage is over, and probably you need to recharge and then go back, and then start. Similarly, while coming back also. So at least 3 times you need to charge your vehicle after 100 kilometers, then at home, and then again while coming back 3 times. But when it is hydrogen based, then probably you need not to refuel. Okay, hydrogen has higher mileage. Okay, you from Indore you can go to Bhopal and come back without refueling, that we will say. So these are benefits of that, but there are challenges in hydrogen infrastructure also. One major challenge is the hydrogen production, and another thing is the safety and security, because hydrogen is explosive, you cannot take any chance of leakage. Okay, yeah, so this is something that we will see. But the good part is, in case of battery and in case of gasoline vehicles, India has foreign dependency. We have to purchase. Okay, when we have one another conference I forgot to mention in earlier discussion, ITEC India, International Transportation Electrification Conference India. So ITEC conference is a basically international version. ITEC North America, ITEC Europe, ITEC Asia Pacific, which happens in China, Korea, and the other part, and another is ITEC India. Okay, so ITEC India is sponsored by IEEE Industry Application Society. I am one of the founding member, and another is SAE India, Society of Automotive Engineers India. Okay, around 200 vehicles exhibitions happens there, and government ministries involved. Okay, so in one of the speech that time, the Ministry of Public Sector Enterprise, Honorable Ananti Giteji, he mentioned that in terms of foreign dependency, it doesn't make any difference if it is a gasoline based vehicles or they say battery based electric vehicles, because in case of gasoline we have to buy from outside, right now Russia or from Iran. Okay, same thing for lithium ion also. Okay, we have to depend on Chile, Australia, China, etc. Okay, so in terms of foreign dependency, it doesn't make much difference. Okay, yeah, so now this slide says that, okay, why government has difficulty in commercialization of electric vehicles. The reason is that electric vehicles are expensive, although the electric vehicle propulsion train is very simple, just a battery, motor, and inverter, that's it. Right, very simple. But you can see here that the propulsion system accounts for 50% of the vehicle cost. So this propulsion system is 50% cost of the vehicle, and then the rest of the vehicle is costing another 50%. Okay, so generally inverter cost is low, quite saturated field, very competitive. Okay, and similarly motor cost is also quite saturated and very competitive. Okay, the major component which is expensive, which is crucial, critical, unreliable, energy intensive, low density and all, very heavy weight, all those issues are coming with the battery. Battery is basically taking major cost in the propulsion system and in the vehicle. Okay, because developing battery takes lots of energy, electricity consumption. Okay, because suppose you are developing some parts, if you are developing a Bluetooth technology entertainment system inside the car, okay, you are developing tires, manufacturing tires, okay, steering, transmissions, chassis, motor, everything, and you are manufacturing batteries. Manufacturing batteries very energy intensive. Okay, that is the reason they are expensive, because battery making itself is costing a lot. Okay, yeah, and so that's why battery manufacturing is very difficult. Okay, the range is limited, density is also not as expected. Weight is also quite high, cost is also high, and environmental issues. Still, the government of almost all countries, including India, they are not able to basically prepare the standards for their recycling or disposals. Even in Singapore, I was talking to the local agencies, Energy Market Authority, Land Transport Agencies, and all that. What is the policy? They say we don't know yet. Okay, yeah. Then what happens after when the battery life is over? And they have disposal issues. Okay, yeah. If you see the last point, I hope you are aware of it, and that is the most critical point. Okay, that making the lithium-ion batteries emits 74% more carbon dioxide than the conventional car. So what this line or what this statement says, that manufacturing of electric vehicle is introducing 74% extra carbon, let us say twice. Okay, so manufacturing of electric vehicle produces 2 times more carbon than the manufacturing of conventional vehicle, gasoline vehicle. So right here the comparison starts. Majority of the people, they ignore this fact that okay, driving electric vehicle is not clean vehicle from the day one, because its manufacturing has produced basically double the carbon. And first of all, you have to compensate for that. You have to compensate for that. And that takes time. That takes time. You have to compensate for that. Okay. So this is one important fact basically to be considered into account, that okay, from the day one, the driver thinks that okay, we are driving clean vehicle, but the government or the manufacturer, they knows no, it's not clean, because the carbon emission has been twice of that. So first of all, you have to compensate for that, and then come to the carbon neutral point. But another problem that happens in many of the countries, including India, China, Poland, and some more countries, okay, that battery is the source of energy for the electric vehicle. But once the battery discharge, who is providing power to the battery? Okay, who is providing power to the battery so that you can drive further? So the battery is not the source finally. The final source is the generation. You will charge your battery by the grid. Okay, now where is the generation coming from? In India, 76% of the generation is coming from coal-based generation. And then the rest 24% is coming from hydro, nuclear, wind, solar, etc. So when you are charging your electric vehicle, the 76% of the component, which is 3/4 component of your charging, is coming from the carbon footprint. Okay, coming from carbon footprint. So what we are doing in our Indian scenario, that probably we are shifting the carbon footprint due to vehicle towards basically carbon footprint for generation. That's what we are doing. Okay, so we say e-mobility or clean electric mobility is okay because it is electric, but clean mobility means no carbon, but actually charging your vehicle needs carbon. Not needs carbon, sorry, it is introducing carbon in the environment, and you are ignoring that fact. Okay, you are ignoring that fact. So this is one research done by Oregon National Laboratory of USA, and here it says that since in United States 23% of the generation of electricity coming from coal fire plant, okay, and then the rest is emitted cleaner energy. So in United States, if you drive the vehicle 22,000 kilometers, then you are reaching the carbon neutral point, okay, which is approximately 2 years, considering 10,000 kilometers per year. Okay, Norway, where more than 90% is hydro and renewable, only less than 10% is the conventional energy generation. So Norway is coming to carbon neutral very soon. Okay, so within a year, Norway can say, okay, Norway people can say we are driving clean vehicle. When it comes to India, China, and Poland, it is 127,000 kilometers. Means after 10 or 12 years. Okay, after 10 or 12 years. Okay, now if after 10 or 12 years, if your battery is gone and you need to replace the battery, then this cycle starts again. Okay, then this cycle starts again. So this is a cumulative process basically to come to the carbon neutral point. So here you can see that in India, China, Poland, or similar countries, carbon neutral or clean mobility will arrive when the generation drops from 76% to less than 25%. Means 50% reduction of coal-based generation. And the government says this is a mission of next 50 years, 2070 and beyond. Okay, I will show you one slide. You will be surprised to see that also. Okay, so now let us see battery-based electric vehicles. So lithium ion is quite popular. Earlier in the past, manufacturers started with lead acid because the cost is very less, 1/10 probably of the lithium ion batteries. Okay, but you can see that compared to lithium ion, if 1 kg, 1 kilogram of lithium ion battery can give you 200 watt hour capacity, but lead acid can give you only 50. Means the density with respect to weight is 4 times high, so that it will reduce basically the weight of the vehicle. Okay, yeah. And similarly, you can see the 1 hour volume. This is the compactness, requires less space. 1 liter volume can be basically 350 watt, but it is 50 only. So 6 times or 7 times high. So because of the compactness and because of the lightweight, lithium ion became popular over lead acid. But lithium ion is expensive. Okay, so Japanese cars like Toyota, they are using nickel metal hydride. So this is a bit less. The density is a bit less compared to lithium ion, but still 3 times high compared to lead acid, and cost is less to stand in the market because people want to buy Toyota. Japan is a brand, and if the car is cheaper, if Japanese car is cheaper, then everybody wants to go for that, and that is the reason they choose nickel metal hydride. Okay, yeah. Now some facts about batteries, including our mobile batteries. Okay, so that's what I was saying, that okay, after 127,000 kilometers, if you need to change your battery, replace your battery, then that cycle starts again. And why there may be a need that you need to change your battery after 10 years? This can be one reason, that if not everybody is an engineer. Okay, not everybody understands all the facts. Nobody is reading the data sheet, manuals and not. Okay, people just want to drive. They see that okay, petroleum is the tank is quite coming to the red zone, the CNG gas is now basically going down, then after that they will start, okay, they cannot go much and they will fill the tank. If you do the same thing with the battery, that is not good for the health of the battery. If you want to discharge your battery quite close, suppose you can see after 85%, when only 15% is left, then you can see in the mobile battery you get the signal, red signal. So you can see 85% or 100% is not much difference. Okay, yeah. Okay, so you can see that okay, only battery will have some number of cycles. Okay, some number of cycles, which is say 1000. But suppose if you are charge your battery and discharge your battery after 30-40% of discharge, you can see the number of cycles becomes 4 times. Okay, so you can see that if you discharge your battery 50%, only half, then you can see the life cycle is 3 times high, or more than 3 times when it is 40%. Okay, so depth of discharge becomes quite important, that not everybody take into account, and because of that you need to replace your battery quite often. Okay, and for countries like Singapore, Thailand, South India even, okay, batteries are good basically in a warm climate. Okay, when the climate is cold, there are two issues. One issue is basically called leakage. Okay, one issue is called the leakage. Okay, what happens that when you go from low temperature to when you go from high temperature to low temperature, battery loses charge. Okay, in Western countries, London, Montreal, New York, and all, and all people don't park the vehicle outside because in the morning they are not able to start the car. Two reasons: either the battery lost charge because of the low temperature, or the electrolyte has frozen basically inside. So you can see it depends upon the battery charge and discharge. If battery is fully charged, then it can withstand a temperature of -8 degrees. Okay, oh sorry, if the battery is fully charged, it can withstand -58 degrees. But if battery, suppose somebody came after driving and came back and put the car outside and slept, okay, and if the battery was basically, for example, if the battery is only 20% charged, then you can see that after at -15 degrees centigrade, the electrolyte, the acid inside will freeze, and then there is no chemical reaction and you are not able to start the car. And this happens very often, and everybody in North America, in UK and all, they basically always keep jumper, stop another car, that okay, can you help me, I just need to boost my battery. That is called jumper or booster. They just put the connector and start the car, and suddenly battery, when the car starts after that. This is quite often basically. Okay, so now this issue of leakage can be basically troublesome in case of winter, because if you started driving and suppose if you meet the traffic, same thing can happen in Kashmir, Himalayas and Uttarakhand. Okay, that okay, when you start the car and if you meet a traffic and the temperature outside is very low. Okay, yeah, there is some noise coming actually, if somebody can mute. Okay, so if and if they meet basically, if they are in the traffic, then what happens, that due to low temperature outside, the battery will start losing the charge slowly. Okay, battery start losing the charge, and if you are driving very slowly basically, then after some time battery charge is over if you are not fully charged. Okay, and then it will close one lane, and then after, the same situation can come to the other vehicles also. If they get stuck in traffic, they lose charge, and now basically they will call the some towing agency to take your vehicle away. Okay, yeah, so this is a serious challenge in winter for electric vehicles. Okay, now coming back to my previous point that I was mentioning, that we have coal-based generation more than 75%, and this is a fact according to Ministry of Coal India, that compared to 2021, in 2022 the coal-based generation has increased by 3.12%. So despite all renewables, despite all solar, wind, floating solar, this and that, okay, still coal-based generation they had to increase. Okay, because of probably the increasing energy demand due to the living standards rise, or due to 7% electric vehicles, e-rickshaws and all. Okay, and some electric buses also. So it is defeating the mission. Like our, as I was saying, that our mission is basically to reduce the coal-based generation, and that is a mission of 2050. But if we increase the coal-based generation this way every year 3%, then probably 2050 is not the right time. Probably we go further beyond. Okay, so we are trying basically for sustainable generation for decarbonization, but however we are in the other direction that way. Despite all our efforts for renewable energy, we are still increasing the coal-based generation. Okay, because current scenario is that the government or the utility has to fulfill the demand, right? Yeah, so just think that okay, right now the electric vehicles are only 7%, but battery based. Okay, when it becomes 100%, another 93% of vehicles converted to electric vehicle, then this will go in some other direction even. Okay? Yeah, because all those vehicles needs to be charged. Okay, now I'm just moving to fuel cell vehicles, hydrogen based. Okay, so it offers all the benefits. Zero emission, of course. Okay, only water droplets. One major point is no dependency on foreign purchased gasoline if it is a conventional vehicle, or lithium ion if it is a electric vehicle. Okay, no need of charging infrastructure at all. Just like the way we have a CNG gas station, we will just have basically a hydrogen station, just refueling quickly. Okay, same thing in this case also, everybody needs to go out because hydrogen is explosive. Okay, no leakage like battery, it is winter, summer, anything, it stays the same. Okay, no charger, onboard charger requirement. Okay, no range anxiety. Okay, you can go 600 kilometers right away in the one refueling of the tank. Okay, major challenges like the way we had a hydrogen sorry, the battery charging infrastructure, and distribution transformers, different cabling, fast chargers. Okay, similarly we need to develop basically hydrogen generation infrastructure and supply to the fueling pumps. Okay, safety is an issue because the gas is explosive, and fuel cell is basically exothermic reaction. Generation of electricity from fuel cell or from hydrogen is exothermic reaction. It produces very high grade heat. Okay, and in India it's already basically high grade heat. Okay, so because of that the car can basically get overheated. So somehow thermal management is an issue. You have to basically excel the air. Okay, in case of aircraft, in case of marine, this is good that you have basically heat generated that can be used for space heating or water heating. Okay, but for the cars it's a different situation. Okay, Yeah. So if we see the fuel cell history is quite old, 200 years old actually, 180 years old, where the fuel cell was generated, and the name given was the gas voltaic battery. Voltaic because output is volt, and gas because it is from hydrogen gas, and battery because battery was popular to produce output voltage, basically DC voltage. Okay. Yeah. But after 60 years, okay, in 1895, after 60 years, people in America, they were successful basically in developing 1.5 kilowatt. So you just see that it took 60 years to develop a 1.5 kilowatt fuel cell, and after that another 35 years to develop 2.3 kilowatt fuel cell. So here you can see this is a 2.3 kilowatt fuel cell, and you can see what is the height of this fuel cell. Okay, the height is probably more than 5 feet, so very large volume. So 2.3 kilowatt, but very large. So in our suppose car, we need basically 10 kVA. So this you need to put 5. Okay, but there is no space to put such 5 fuel cell in the car. The volume of this 5 fuel cell itself is basically similar to a car. Okay, but it was developed, and in 1930, in 1950, NASA basically deployed them and sent for space mission, Apollo lunar mission and Gemini space mission. Okay, ensuring that fuel cell are quite safe. Okay, quite safe in 1930 and 1950. 70 years from now, 90 years from now. Okay, so fuel cell technology that time also became quite matured, quite a, I mean, 90 years back, almost a century. But the major challenge was basically like this volume and the weight and all. Okay, that you cannot fit inside the car, inside the buses also. Okay, but okay, we'll see later. So out of several, so fuel cell, when we talk about fuel cells basically are a number of fuel cells. Okay, so which one is the right fuel cell, that also needs to be determined. Okay, generally proton exchange membrane fuel cell is popular for for this transport application, or even for the standby backup power supply. Because one thing, if we talk about transport, the major reason is that, okay, this is the low grade heat. The temperature of proton exchange membrane fuel cell, the heat they generate at temperature is 50 to 90 degrees. But if you see solid oxide fuel cell, 1000 degrees. Okay, phosphorus reactant fuel cell, 200 degrees. Alkaline fuel cell, 200 degrees. Molten carbonate, 600 700 degrees. You cannot stand that. So only two possibilities for for fuel cell cars, either proton exchange membrane fuel cell or direct methanol fuel cell. But direct methanol fuel cell, the fuel used is basically methanol, which is CH3OH. So CH3OH has basically carbon C inside. Okay, so when it reacts with the oxygen, then emits carbon dioxide. Then we cannot say direct methanol fuel cell based electric vehicles are zero emission or clean vehicles. So only zero emission vehicle possibility is proton exchange membrane based fuel cells. Okay, but when it comes to marine applications and more electric aircraft application, they generally prefer solid oxide fuel cell, because they can use the high grade heat for the space heating and the water heating, because at 40,000 feet above, it's very cold, and similarly inside the ocean, it's very cold. Okay, yeah. So after 1950, as I was saying that, okay, the technology was not mature enough, because the fuel cell were quite big and quite heavy. Okay, so they could not be used for electric cars and in the electric buses. But after 40 years, they were able to they were successful in developing very compact and lightweight fuel cells. So here you can see the 250 kilowatt of fuel cells and running the fuel cell bus. Okay, yeah, Mercedes-Benz. Okay, similarly you can see eBay. eBay is basically the bidding company, like it sells products basically like Flipkart and Amazon or Alibaba, etc. Okay, but in eBay you can bid. When a product is there, a price is written, you can bid basically that I want to buy on this price. Okay, so generally for backup power system, we use UPS or we use batteries. In 90s, eBay used basically fuel cells, 6 megawatt capacity. Okay, quite large. So 30 years from now, the fuel cell technology was quite matured in terms of high power scaling, megawatt level, and quite compact, basically quite safe and lightweight. Okay, either for stationary backup power generation or for the mobility application. Okay, after US, then it spread around basically in Europe, which is 12 years from now, 2010, we are in 23. So in Italy, Switzerland, Germany, London, which is UK, Oslo, Norway. Okay, Almost majority of the European Union, basically they used electric buses for their local transportation. Okay, in Canada in 2008, yeah, in 2008, when the Olympics or Commonwealth Games were there in Vancouver, British Columbia state, they used hydrogen fuel cell buses basically for the picking up and dropping of the players and the coach from the hotel to the playground and then back in 2008, 14 years from now. Okay, Canada also tested it. Okay, now if we talk about UK, we were talking about 2010. Now if we talk about 2021, which is 1.5 years before, London local transportation has been fully on hydrogen buses now. If you do a Google search or if you open BBC or other websites, London is using around 25 buses. You can see this is a single bus, and you can see behind is the double decker bus. Okay, the London local transportation has been fully hydrogen based now, and uh, the bus starts 6 o'clock and goes back to garage 1 a.m. in the night. Means 19 hours of running without refueling. Just think, battery based buses cannot do that. You need basically 3-4 times charging. But 19 hours without refueling, 6 o'clock and 1 a.m. after that. Okay. Yeah, just 1.5 years before. Okay. In India, 2018, IOCL in collaboration with Tata Motors also developed and tested fuel cell bus, but because of the security issues and the lack of hydrogen infrastructure, they are not in use yet. Okay. Yeah. Now, this is the major opportunity or the major launching happened in India last year, March, which is probably from 10 months from now. Very recent, very new. That Ministry of Transport, Honorable Nitin Gadkari ji, he is very keen on hydrogen. He's very keen on hydrogen. So on 16 March, he basically launched Toyota Mirai, which is Japanese based company. So Toyota Mirai, but don't think that okay, Toyota Mirai is a adventure of 2022. Toyota Mirai is probably 6 or 8 years back, probably 2014. So Japan tested it 8 or 10 years before and using it, Toyota Mirai. But in India, it was launched last year. Okay. Now, as I was saying, it can go 600 to 700 kilometers. So from Jaipur to Delhi and back to Jaipur, Indore to Bhopal and back to Indore, right? Hyderabad to Warangal and back. But in electric vehicles, battery based, we cannot do that. Okay, 600 kilometers. And minister says, which is true, that it will open scope basically for trains and planes also in future. Okay, that I have some slides for that. Okay, and huge opportunities for farmers, because the dirty water coming from the irrigation can be reused basically for hydrogen production. Okay, similarly, any kind of waste or any water from the ocean water also, now technologies are there that without filtering you can use the ocean water also for the hydrogen generation. So you need not to be dependent upon the foreign purchased gasoline or the lithium ion. Okay, making India independent. Okay, yeah, because political situation changes. Okay, yeah. So, and the hydrogen can be produced from the renewable energy. We need not to be dependent basically on the grid only all the time. Okay, and future that okay, train, aircrafts, they all will be hydrogen powered. That's what he said also, and which is true. Okay, that I will show. So earlier in 2010 to 16, as I was showing you one slide, that couple of buses were there because only Toyota Mirai. So you can see Toyota Mirai, as I was saying, it is 8 years of adventure. So Toyota Mirai was launched in 2014, okay, in India in 2022, and Hyundai. But now you see in 2021 and later, all the manufacturers basically are focusing on hydrogen vehicles, selling or not, but at least they are testing that okay, yes, they have the capability to develop and test and develop and basically sell also in future whenever the sale increases. Okay, yeah, and quite a few they sold already. Okay, quite a few they sold already. Okay, now when we were talking about that, okay, there are scope for trains and as well as for aircrafts. So you see, in Germany already from 7 years back, from 2016, the name of the train is called Coralia Island, that is developed by Alstom. So right now, all the contracts about hydrogen vehicles, either it is trains in Germany or even in UK or even in India, I will show you one slide. All the contracts are going to Alstom. Okay, Alstom is having lots of business nowadays because of the hydrogen. Okay, so in 2016, Germany has basically hydrogen based electric train fully on hydrogen. Okay, 2016, 7 years back. Scotland, that after 2035, all the train network of Scotland will be basically on hydrogen. Again, the same. Alstom, Coralie Allen, they have given the contract. Okay. Now, this is the news of last year, August, which is 6-7 years back. Okay. 2016, one train, and now you can see another 14 trains started in Germany, hydrogen powered. So now Germany has basically 15 hydrogen based trains. Okay. And another 27 to start in near future. Another 27. Coralie Island. Germany is also moving towards full hydrogen-based electric train network. In Europe, the major source of local transportation as well as inter-country transportation. Suppose from Germany, you want to go Netherlands, you want to go Australia, you want to go Denmark. It's all through the train usually. Okay, very comfortable. You want to go to Switzerland, you want to visit Switzerland. It's all railway transportation is the most popular. Not even driving, not even, like car. The flights are not that popular, and because of that, flights are very cheap in Europe. If you want to go from Germany to Rome, you can go in 50 euros, because generally people prefer train because trains are very cheap. So flights are also matching the cost of the train. Okay, very cheap flights in the Europe because of that. So German network railway network is going to be fully on hydrogen. Already 15 and more to come. Another 27 to come in a couple of years. Okay. In December also, Indian Railway Minister announced that in December 23, so not very far, another 10 months, which is still ambitious. But if not in December 23, but at least in 24, you can see the order is again given to Alstom Coralie Island. Then we will be having hydrogen train in India also very soon. If not this year, December, at least next year. Okay. India is moving towards hydrogen economy, right from the Toyota Mirai, the passenger cars to basically the electric train. Okay. So now, if we see that why the hydrogen was not popular, safety, security was one issue, but the production of hydrogen was also energy intensive like the battery, and the major reason was this compressor. Because once the how to develop hydrogen, produce hydrogen is basically the water is basically decomposed through electrolyzer. Okay, so very soon electrolyzer is going to be also big business in India. Okay, so startups and majority of the industries, they will start producing electrolyzers. Okay, I will show you one slide what is the reason for that. Okay, so electrolyzer should be basically hybrid. It should be able to take power from the solar, from DC, as well as from the AC, from the grid. Okay, it should be hybrid. Okay, that is quite possible. So water is decomposed into oxygen and hydrogen, and then hydrogen is basically compressed by the compressor to fill in the cylinder. Because hydrogen is the gas, and the property of gas is expansion. Okay, if there is a 10-liter cylinder, and basically if you put 1 liter of hydrogen, then 1 liter will also take entire space of 10 liter. So you need to compress with high pressure, so that 1 liter will take 1 liter space, so that you can fill another 1 liter, another 1 liter, and you can fill basically 10 liter in 10 liter. Okay, so generally if you see these CNG gases, hydrogens and all, they are not sold in liters, because you cannot like the people cannot say that, okay, in the cylinder do you have 10-liter hydrogen or 1 liter hydrogen, because it takes the entire space. But if you can wait, then only you can say that, okay, how much hydrogen is inside. That's why the selling of the gas, basically either the compressed air, CNG gas, hydrogen, they sell in kilogram, kg. Okay, yeah, because hydrogen or any gas, basically CNG and all, gas takes the entire space, because they expand their property of expansion. So they need a compressor, and compressor is energy intensive. Efficiency is very less, extremely less. Not like motors or inverters, 96%. Very less efficiency. Because of that, the process was energy intensive basically. So generating hydrogen was taking lots of energy, and that is coming from the coal. Then basically it doesn't make much sense. Okay, so now this basically goes to the filling station similar to CNG or the gasoline, and then basically fill inside the vehicle. But after that, if you see the lower portion here, you can see that high differential pressure electrolyzers has come. Earlier, if you see here, that mechanical compressor was basically causing high losses for hydrogen compression. Okay, because it develops high pressure to like say 35 megapascal to basically store hydrogen, compress hydrogen inside the tank or cylinder to basically fill 10 liter in 10 liter. Nowadays, this is integrated inside the electrolyzer, and this is known as high differential pressure electrolysis process. Okay, that electrolyzer itself is basically is able to develop or basically able to discharge, okay, high pressure hydrogen. So this high pressure hydrogen directly goes and fill 10 liters in 10 liters, 35 megapixel for example. So that way you avoid the compressor loss and the overall process of electrolyzer and storage becomes energy efficient. Okay, so this open scope basically for hydrogen production and the hydrogen economy, because the compressor is out and you are able to do hydrogen production efficiently by high differential pressure electrolysis. Okay, so if we talk about infrastructure, as I was saying, that this is a major challenge. So it is limited still, but still available. 35 in Japan, 18 in South Korea, and in 12 in UK. But I'm sure 2021 they started in London so many buses, so probably it should be more. California 25, and probably a lot in Europe now. Okay, earlier it was 10 in European countries. Okay, probably now it should be more. Okay, yeah. Singapore also said that by 2026 they will be having 600 megawatt capacity of hydrogen infrastructure, okay, in Jurong Island. But actually another news is about to come, that in another island of Singapore that is known as Semakau, they will again have quite like, if not 600 megawatt, but 100 or 200 megawatt of hydrogen station. So Singapore is also moving towards basically hydrogen plant or hydrogen generation. Okay, just the first week of January, Prime Minister Modi, he also announced that India is going to be a global hub for hydrogen. Okay, and 20,000 crores of investment has been sanctioned to make India basically global hydrogen hub. Okay, India is also moving in that direction. So as I was saying that this is the mission, that by 2050 the majority of the country have to cut their carbon emission by 80%. Okay, and that is the reason that generation as well as the mobility is moving towards basically electric, decarbonized, because moving generation to renewable and moving basically mobility to electric or clean mobility, this 80% cut is possible. Okay, yeah. So now if we see the enabling technology for fuel cells vehicles or fuel cell systems is power electronics, because fuel cell basically develops variable output DC voltage. Okay, variable output DC voltage, and that variable is highly variable, not like battery, not like solar. Okay, battery variation is basically only 13%, 13, but fuel cell variation is more than 100% variation, or quite large variation. Okay, that we can see from here. Okay, so now compared to the battery based electric vehicle, the fuel cell electric vehicle also has similar component, power conditioning unit, okay, which is inverter, electric motor, induction motor, synchronous motor, controller, okay, energy management, EMS or battery management system. Okay, but this is extra thermal management because of the exothermic reaction. As I said, fuel cell is taken hydrogen tank instead of battery, but still a low capacity battery is required. Okay, why low capacity battery is required? Because fuel cell response time is quite high. When you want to start the vehicle, fuel cell is starting is not an easy process. It takes time, few seconds, 1 minute even. Okay, so when you start the vehicle, so what happens? It starts from the battery. So when you start running it, probably first 1 kilometer is on the battery, and after that fuel cell takes over. Okay, when it is normal driving or in a steady state driving, then basically fuel cell is supplying the traction power or the propulsion power. And when you want to accelerate, then again the fuel cell will not be able to supply the power instantly, because fuel cell time constant is large, because a mechanical process is involved to adjust the valve opening, the throttling of valve, as well as the electrochemical reactions that will decompose hydrogen into 2H plus and 2E minus electrons. Okay, so that takes time basically to come to the equilibrium stage, as well as the mechanical valve adjusting based on the speed requirement. Okay, so that time the power is supplied by the battery, and once the fuel cell is able to supply, when the electrochemical reaction at equilibrium and the mechanical valve positioning has been adjusted, valve opening basically, then a battery will be idle and fuel cell will take over. So for start, for acceleration, battery is required for a few seconds or 1 minute. Okay, similarly when it is deceleration or the braking, then during regeneration, then motor acts as a generator, and then basically battery will be charged. Fuel cell is not reversible. Fuel cell is unidirectional. So basically, where the power during the power capture during regeneration will go, it will basically go and charge the battery, and then the battery can be used again for the acceleration and again for the starting. Okay, so battery is necessary. If not battery, then some people use ultra capacitor also. But ultra capacitor problem is that ultra capacitor volume for the same energy is quite higher. Okay, because ultra capacitor basically has low energy density, battery has high energy density. But ultra capacitor advantage is ultra capacitor has high power density, means it can supply higher peak power. Okay, transient power basically. Okay, but because of the energy density, batteries are popular compared to the ultra capacitor. Okay. Yeah, and batteries like ultra capacitors are also scalable, but sometimes ultra capacitor, when you connect in series to develop the higher voltage, their internal resistance becomes quite high compared to the batteries. Okay. Yeah, so battery is still a requirement as an energy buffer or as a secondary source of energy in fuel cell vehicle because of the transient condition, starting, acceleration, and regenerative braking. Okay, somewhere if it is not preferred, for example, that okay, fuel cell response time is quite slow and fuel cell, because hydrogen production is not that matured yet, so instead of propulsion power, fuel cell still can be used in the vehicles, in the electric ship, or in the more electric aircraft as an auxiliary power unit. You can supply the hotel load, the lighting, the cooling, air conditioning, entertainment system, displays, mic addressing system, that can go fully basically on fuel cell auxiliary power unit. Okay, and the propulsion with the heavy load can go basically on the batteries or on the basically on the batteries. Okay, and a part of the other load, which is known as hotel load, basically can be on the fuel cell. So fuel cell are also popular basically if we see the earlier literature for auxiliary power unit, because earlier where fuel cell were basically quite big. Okay, as I was showing you, 5 feet, and the volume was quite large, so they were basically used for auxiliary power units. Now because of their compactness and lightweight, they are basically being used for the propulsion system also, but still there is an option. Okay, yeah. So now if we see that okay, how to design the power electronics or what kind of power electronics, so it depends upon the fuel cell characteristic. You cannot replace the battery by the fuel cell keeping the same inverter. The inverter that you are using for battery based electric vehicle cannot be used for fuel cell vehicle. Here is the reason, you can clearly see. One reason is that fuel cell voltage changes a lot. Battery voltage changes only 12-13%. Okay, if you are using a 400 volt battery, the minimum voltage is basically around 350 when battery discharges over time. Okay, yeah, if it is 450 volt batteries, it can come down to basically 390. Okay, yeah. So if you see here that okay, when the fuel cell is at, when the vehicle is at higher speed, the rated speed, say for example 100 kilometer per hour, the fuel cell voltage is say 400 volt, drawing say 10 kilowatt power, for example. Okay, and when suppose you are driving in the somehow traffic is there and the speed is only 40 or 50, which is quite which is the regular speed, 40-50, when you are in the city driving, not the on the interstate highway. And when it is 40-50, then you can see the fuel cell voltage is around 650 or 700 volt. So you can see, if you are driving on high speed, which is on highways, fuel cell voltage is 400 volt. When you are driving inside the city, okay, fuel cell voltage is 700 volt. If you got stuck in the traffic, okay, then it is 800 volt. So fuel cell voltage has a large variation. So you cannot use the battery inverter. The devices will damage. Okay, you need to prepare an inverter that can handle the voltage variation from 400 to 800 volt. Okay, yeah. So this is something that we have to design a power electronic that can handle this voltage variation. And another is basically hydrogen utilization. Okay, that let us see the next slide. Okay, what happens that each basically current level, which is basically speed of the vehicle, corresponds to a particular hydrogen flow. For example, 10 ampere on highway corresponds to 100% of the flow, means the throttle valve is fully open. When you are doing the city driving, speed is 40-50 km per hour, then hydrogen fuel flow should be 50. But suppose if your mechanical valve is defective, or suppose some problem has happened, that at 40-50 speed, somehow it is not able to adjust to 50, but suppose it is 75, for example, rather than 100, 75, it adjusted a bit. but still there is a 25% of hydrogen wastage. Then what happens? Instead of 600 kilometers of driving, you will be able to drive only 400 kilometers. Okay, you will be able to drive only 400 kilometers. So what happens that each speed or each current of the inverter has basically one hydrogen flow point. So the mechanical valve should be able to adjust to that value. If not, then this is called basically waste of hydrogen or low hydrogen utilization. Okay, so the way we have a maximum power point in solar, we have basically the optimal power point for, corresponds to the hydrogen flow. It is the reverse. In earlier case, what happens? Based on the intensity, you define the current. Based on the solar intensity, you define the current or power. But here it is different. Based on the current, you decide basically how much hydrogen flow should be there in the reverse direction, but it is still there, maximum power point. So based on that, the controller should be able to give a command to the mechanical system there to adjust this hydrogen flow. Okay, yeah. Sorry, what happened? What happened? This. Okay. Yeah. Sorry. Yeah. So this is number one is this voltage variation, and number two is basically the hydrogen adjustment. So you can see from the next slide that if this hydrogen adjustment is not okay, then you can see. So yeah, so that's the third point that I will explain. So that will explain the first one also. The power electronics or the inverter should be such that it draws the stiff DC current from the input from the fuel cell. Because if the current drawn from the fuel cell is basically having a ripple, then hydrogen flow adjustment is corresponds to the peak value. But the power transfer to the load or the mileage given by the vehicle corresponds to the average. So from the average to the peak is basically waste of hydrogen. So if you have a ripple free current which is similar to the average, stiff DC current, then mileage is quite high. If there is a ripple, mileage basically will start shrinking. Okay, and if the ripple is more, mileage is less, because hydrogen flow is suppose this current corresponds to 50% of the speed, but if there is a ripple, so hydrogen flow corresponds to 60% of the speed. Okay, so there is a 10% of wastage. So instead of 600 kilometers, probably you will go 500 kilometers. So that's why you can see from the figure on the left hand side that if the ripple is very close to 0 or 5%, you can see hydrogen is utilized fully, and hydrogen electrical efficiency is 50%. The rest comes from the thermal. Okay, similarly, if you can see that if the ripple is quite large, for example 25% ripple, okay, then you can see that hydrogen utilization is around 80%. Okay, and the fuel cell efficiency drops from 50 to 40%. If the ripple is 80%, then you can see that the hydrogen utilization is 60%. So instead of going basically 600 kilometers, we will go quite less than 300. Okay, so if ripple is like this, 0 to 20, 20 to 0, 0 to 20, 20 to 0, 100% ripple, the hydrogen utilization is 50%. You only go 300 kilometers. Probably you will feel that, okay, my vehicle has a problem, or there is a leakage of hydrogen from the cylinder. No, there is no leakage. Filter is not okay. That's it. Okay, filter is not okay. Or another problem is that mechanical valve is not okay. The controller, you are not basically able to adjust the valve position, the throttling valve position correspond to the current requirement or the speed requirement. It is higher than that. That's why the extra flow, leakage is basically causing this less mileage. Okay, so here is the leakage. Okay, and here is the filter. Okay, so we need a power electronics that can handle this large variation with the speed. Okay, that can basically manage this optimal power point. Okay, and then basically that can maintain a stiff DC current. Okay, these three are the major requirement. You cannot use the battery based inverter for the fuel cell vehicles. Okay, so generally these three are the major requirement, and another one we can see the transient operation, that okay, the power electronic inverter should be able to switch between the battery and between the fuel cell. When it is steady state, then fuel cell. When it is transient condition or regenerative braking, then it is the battery. Okay, yeah. So generally there are two kind of power electronics. Okay, we are coming to end now, probably the next two slides. That there are two kind of power electronics. One is voltage fed, one is current fed. Current fed power electronics, which is my research area. Okay, I got my IEEE fellow because of this. My majority of the publications are on current fed converters. Okay, very novel papers. Okay, out of 300, probably 200 are on current fed systems. So it has inductor in series with the source, and inductor is basically develops stiff DC current. Okay, because inductor is a current source thing basically. Okay, so here is the stiff DC current. So right away the first problem of ripple free current is solved. Another is basically that okay, the adjustment of hydrogen should be corresponds to the input current or according to the speed. Okay, so this input current will right away give the command basically that okay, it should be 50% or 80%. If there is a ripple, that command is changing. Okay, so those two problems are solved right away. Okay, another is basically large variation in voltage and current. So I have written one paper also that I compared the voltage fed resonant converters, voltage fed PWM converters, voltage fed bidirectional dual active bridge converters, voltage fed converters with inductive filter, with capacitive filter, with current fed converter. And after that there is a judgment that if there is a large variation in the voltage, current fed converter can give you a relatively flat efficiency curve. Voltage fed converter efficiency drops down. Okay, so after that my citation has gone more than 6,000 now. People started working a lot on current fed converters. Okay, for especially fuel cell applications. Okay, so these are the two legends. One from Tesla, Elon Musk, who is a big fan of battery-based electric vehicles, and he says that okay, fuel cell or hydrogen fuel cell is bullshit because hydrogen is dangerous. Okay, another legend, he says I don't care about Elon Musk. So you can see that one legend does not follow another legend. Okay, but both are quite successful. Okay, these legends can come from the basically startups also. If they can get a novel idea, they need not to follow the Bob Carter or the Elon Musk. That novel idea basically can fail the ideas of these two also. There is a possibility. Okay, so we have lots of scope for startups when hydrogen economy moves in India. Okay, so that is all from my side. Thank you for patiently listening, and I will be happy to take any queries now.
Rinky.
Yes. Sir, thank you so much, sir. That was a very interesting and informative talk. We have few questions for you. I'll just read it one by one from the chat box. So, one is by Mr. Anubhav Sharma. What is the role of a battery in a fuel cell based electric vehicle?
Yes. So as I had mentioned one of the slide, that fuel cell response time is low. Oh, sorry, fuel cell response time is high. Time constant is high. Because of that, it does not respond to your acceleration request. It cannot take the regenerative power. It cannot start on time. Okay. So because of that, battery is required to support the propulsion system during transient, during acceleration, during the start, as well as to capture the regenerative power. So that is the major reason of battery requirement in a fuel cell vehicle. You can replace the battery with ultra capacitor also. There is an option for that, but ultra capacitor volume is larger. That's why people prefer batteries.
So the next one is from Mr. Manoj Badoni. Can hydrogen production lead to affect water security?
Okay, so now let us compare with the lithium ion. You might have heard basically that now Jammu and Kashmir has lots of lithium. Okay, Chile is number one. Chile in South America is number one in entire world. But I hope you know that mining lithium material from the earth takes lots of water, and that can cause water scarcity. So this is the problem with the procuring mining lithium material in Jammu Kashmir also, that it can cause water scarcity in that area because tons of gallons of water required for the mining of lithium ion. So right now the same problem, the same consideration is there when you produce the hydrogen, but it is lesser than the mining of the lithium ion material. Okay.
So I also have one question in this regard also. Like, what is like the amount of water and the hydrogen that you get from? There might be some ratio, something like data, like how much is the water? This much of liter is required to generate this much of the hydrogen gas.
That I have to look into in terms of
Okay.
yeah. So probably through email we can discuss this further. Yeah.
Okay, okay, no issue.
But one thing is for sure that mining lithium ion requires more water.
Okay, okay, fine.
Yeah.
So next question is from Sir JP Das. What is the cost effectiveness comparison?
So compared to lithium ion batteries, we can say probably now quite competitive. Okay. At one point of time, fuel cell used to be extremely expensive. Okay. And only one or two companies were making fuel cells, like Ballard and Hydrogenics, and then after that, Bloom Energy came in. Now Alstom and many others. Okay, or probably a bit higher still, probably a bit higher still. But when it comes to the major motive, what is the major motive? If major motive is basically, if you see by 2050 reducing the carbon reduction, okay, not just the cost, government has to give the incentives to reduce the cost of the vehicle. Where the motivation is to reduce the carbon content, then as I said, you cannot go with the lithium ion vehicles because it produces 74% more carbon, defeating your objective. And the charging from basically coal-based generation is again defeating your objective. So when it comes to your motivational, basically, right now, for example, Singapore does not generate coal-based electricity at all because it is carbon-based. Okay, it generates only natural gas-based. The cost of electricity is high, but still, because motivation is okay, Singapore should not be polluted. Okay, so it goes with the motivation basically, that how it affects the health, it affects the tourism, and many other things. Okay, so because of that cost, it may be the fuel cell may be maybe costlier, but producing less carbon compared to lithium batteries, less energy intensive.
Okay. So the next question is from Mr. Malik. What is the power consumption for the water electrolysis?
Oh, it is quite efficient. The majority was so if you see the electrolyzer efficiency is quite high actually. It is a power electronic component overall. The major challenge was basically the compressor, and now with the high differential pressure electrolysis, that has gone.
Okay.
Because compressor efficiency is very less, probably 40-50%.
There's one more question from Mr. Vijay Kumar Dubey. Is it the hydrogen which are generated through cryogenic process or electrolysis?
Both. Okay, both. So through electrolysis is popular. Okay, through cryogenic process also many countries are doing it, including Australia. Okay, and the hydrogen generated through that process is quite popular in marine industries. So the answer is both, but the carbon neutral process is basically electrolysis, which is popular. But yes, to answer is yes to both in principle.
Okay. The next question is from Mr. Vineet Ahuja. For storing 1 kg hydrogen, how much volume of tank is required and how many kilometers an electric vehicle can run in that? And how we can decide these parameters?
I think 1 kg can go probably 40 to 60 kilometer, 1 kg of hydrogen. Yeah. And the cylinder requirement, probably generally the kg and liter is more or less quite similar. So probably 1 kg may require 1.2 liter of cylinder, in my opinion. I do not have the exact number, but kg and liter are quite similar in numbers. 1 kg you can store probably in 1.2 or something, not 2 liter, definitely less than 1.5. Okay, 1 kg can store in that. So this is like a thumb rule kind of thing I can say today, but probably we can search and find this out, that how much this is a good question actually, that how much space is required. But 1 liter 1 kg can be stored in 1.2 liter of volume or something, and can go probably, in my opinion, nearly 40 kilometers easily. CNG can go, I think, 20 kilometers for now.
Okay, the next question is from Mr. Manoj Badoni. Why voltage fed converters are not suitable for fuel cell based electric vehicle?
Because actually you see the property of inductor, if you see inductor versus capacitor, the purpose of the capacitor, in fundamental, the purpose of the capacitor is to develop stiff voltage, not the stiff current, and the purpose of the inductor is to develop stiff current, not the voltage. Okay, so that's why inductor is meant basically to give you flat current. The capacitor will give you basically the flat voltage, but because of the high frequency operation, okay, the ripples can still appear, but inductor will basically flatten everything. Any voltage variation, inductor will flatten everything. Voltage fed converter will not be able to do that in principle. Okay, and number two, electrolytic capacitor is less reliable. Electrolytic capacitor has life. Okay, after 2000 cycle, after 10 years or something, electrolytic capacitor will fail and you have to replace. Okay, inductor do not fail for 20-25 years. Another thing that I was saying, voltage fed converter, as the voltage changes, they don't respond well. They respond very well to the load current changes. If the power is 10 kilowatt, power is 5 kilowatt, power is 1 kilowatt, voltage fed converter will respond excellently, very nicely. But as the input voltage changes, voltage fed converters are not friendly to the source. They are only friendly to the load. I can say that way. Current fed converters are friendly to both. As the source voltage changes, inductor inductor can, what is the purpose of inductor? It can handle the voltage fluctuation to make the current constant. That's why between any two voltage sources, inductor is connected. You cannot connect capacitor between two voltage sources, very high inrush current, right? But inductor will flatten basically any two voltage sources. Okay, so that is the reason that basically it gives you flat current despite any voltage variation and give you higher efficiency when the voltage changes.
The next question is from Professor Ashish Kumar Singhal. Can we use other converters for fuel cell?
I mean, nobody
the same.
I mean, nobody stops. So there is no rule like that that you cannot use. What happens that manufacturer, they compare two things. One thing is the initial cost, which is today. Okay, this I learned recently actually when I was doing my research. Even I was not taking this factor into account. Whenever one manufacturer buy from another manufacturer, there are two kind of cost associated. One is cost initial or investment cost. Another thing that I was also not aware of, and many of us do not care in our research, that is called LCC, life cycle cost, 20 years of operating cost. Okay, suppose today if you pay $100 high or 5,000 rupees high, we are worried about that. But in 20 years, if every year, for example, you are paying 1,000 rupees higher in maintenance or because of the low efficiency, you are paying 20,000 rupees more. So overall, basically, you think that, okay, by paying 5,000 more, it is expensive. No, it is 15,000 rupees less expensive. So life cycle cost is more important than the initial cost. That also I learned in my recent study. Okay. So that is the reason that, okay, which converter to buy today is not based on basically the cost. They go basically with the efficiency and many other data that overall 20 years of running, which one is better, which one will save energy, which one will save basically the cost.
The next question is from again from Mr. Manoj Badoni. What about the dynamics of fuel cell based EV as compared to the battery EV? And by the dynamics, he means the response time.
Yeah, the battery response time is higher compared to the fuel cell. So what happens that whenever the dynamics happens, okay, whenever the dynamics or transients occur, it is the battery which will respond. Fuel cell does not respond to the dynamics at all in any fuel cell application. Either it is stationary or it is mobile. Okay, only the one that is responding is the battery. Batteries are deployed for that responding during the transient or dynamic conditions. Fuel cell is only for steady state. It changes from one steady state to another in a smooth way, and during the transient period, basically for seconds or for minutes, battery will come into picture, and when it is new steady state, then battery will be out of the picture.
The last question is from Mr. Malik. The controlling of a mechanical valve with respect to electrical ripple, as there is a difference in the time constant, how is it possible?
No, there is no difference in time constant. I mean, as I said, that there are two processes involved. One is the electrochemical. That itself basically takes time. And this is another additional to that, basically, because there is a mechanical system. Electrical system, suppose, based on the solid state devices, MOSFETs and IGBTs and all. In millisecond, they respond, right? Mechanical valve does not respond in millisecond. Okay, so this is the difference.
Okay, so thank you so much for giving appropriate answers to all the queries. And now I hand over to Akhilesh for the further proceedings.
Okay, thank you, sir, for giving so enlightening on this aspect, which was, I mean, it is not very well much explored in India. Now I request Dr. Sramani to present the vote of thanks.
Yes. Today I have the privilege to propose the vote of thanks for this wonderful and informative talk. Firstly, I would like to thank Dr. Akshay Rathore for sparing his valuable time and agreeing for this talk. I would thank Dr. M.K. Badapanda for his continuous support and guidance for arranging such webinars. I would like to thank Mr. Akhilesh Tripathi and Ms. Rinki Upadhyay for ensuring the smooth functioning of this webinar technically. I would also thank Shri J.P. Dash, Deputy Director General, Ordnance Factory Board, and Shri Anand Kulkarni from Indian Navy for joining this webinar. I would like to thank Dr. Rajesh Nema, Shri Y.P. Singh, Shri T. Paul, Shri Sumit Karale, and Dr. D.V. Ghodke and Dr. Trapti Jain for being with us in this webinar. Last but not the least, I would thank the whole IEEE Madhya Pradesh section community and all the audience present over here for making this talk a wonderful success. So, thanks to everyone once again.
Thank you, everyone.
Okay, so sir, I think we can close this lecture now.
If you want, we can take some few photographs
Yeah,
of the like.
Yes.
Really nice lecture.
Thank you.
All may come in video mode. You can take few photos now.
Hello, Lalit. All good in Raipur?
Yeah. Okay, we may stop now.
Thank you, sir.
Yeah, thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
sir.
Thank you. ठीक है आशीष.
Thank you, sir. Thank you.
Okay, I'm now closing the meeting. Thank you.